All right, here we go with Unit 2. We're still looking at molecular and ionic compound structures. And in this topic, Topic 5, we're going to look at Lewis dot structures of covalent compounds. So we will use the octet rule and exceptions to the octet rule in order to draw Lewis dot structures of covalent compounds. So Lewis dot structures of atoms. A Lewis dot structure is a representation of the valence electrons of an atom. So the valence electrons are found using the columns of our periodic table. So let's review our valence electrons. Anything in group 1 will have 1 valence electron. Group 2 will have 2. We are going to skip our transition metals, these guys, for now. There's no pattern to those ones, so we're going to skip it. Over here on the right side, group 13 has 3 valence electrons, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and group 18 has 8. The only exception to any of this is helium, because it only has 2 electrons, it only has 2 valence electrons, because it just has that 1s orbital. So our valence electrons, we can draw our dot structure based on those numbers. So we're going to do period number 2. We're going to do all the elements in that. So lithium would have 1 valence electron, so we draw that 1 dot. Beryllium would have 2, so we're going to draw 2 dots and separate them. Boron would have 3, and I always start at the top and I put 1 on each side, kind of like there's a box around it. Carbon would have 4. Nitrogen would have 5, so this is where we can start pairing them up. Just like our electrons, we separate them before we pair them up. We do that here as well. So nitrogen has 5, oxygen has 6, so we're going to separate the 4 and then pair the next 2. Fluorine has 7, so separate and then pair them up. I'm at school, so the bell just rang. All right, and neon has 8. So we have our 4 and then our paired, oops, that one got a little weird, paired electrons. So there's our 8 electrons for neon. So this represents our number of valence electrons, and this is just for the atom themselves. And we're going to build into making dot structures for molecules. All right, we're going to start with really basic molecules, our diatomic molecules. So a couple things about terms. Molecule refers to a covalent structure. Okay, so we can have a covalent molecule, or we can have a ionic compound. All right, covalent molecules, ionic compounds. So in terms of words and vocabulary, that's what we always want to refer to molecules as covalent substances. Our diatomic molecules are things with 2, di meaning 2, atomic meaning atom. So they're molecules made of 2 of the same atom or same element, and they always come in pairs. So there are 7 of them. These naturally occur in pairs. So if we go into nature and we find just bromine, we're not going to find bromine atoms. We're going to find bromine molecules, Br2. There are 7 of these. They are the Hofbrinkel elements, so you might have remembered that crazy term from last year, but if you've never heard of it, it stands for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, are 7 diatomic elements. So if we want to find them on the periodic table, there's another way we can locate them. If you go to number 7, which is nitrogen on the periodic table, and then draw a 7 through those elements, you'll have nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That's actually 6 of the elements. There's 1 left. The 1 left happens to be number 1, which is hydrogen. So there are 7 diatomic elements. Start at number 7 and draw a 7. And then there's 1 left, which is number 1. Don't know why it works, but it works. So if we want to draw their molecules, we're going to base it off of their number of valence electrons. So hydrogen is 2 H's, and they each have 1 valence electron, so we have 2 electrons total. So to draw its structure, we can imagine that having hydrogen with its 1 valence electron for each one, we want to pair up electrons to form a bond. Well, we've got 2 electrons, that creates a pair, so this would create a bond. So hydrogen is a single bonded substance. I can simplify and kind of draw it neater that way. So that's our hydrogen molecule. That's what's in the air all the time. If we have hydrogen gas, we have H2. Bromine, each bromine atom has 7 valence electrons, so we would have 14 electrons total to use. So bromine, if I drew just the dot structure of one of them, like that, we would see that we have one unpaired electron. Well, each bromine would be the same. They would each have that one unpaired electron. So those 2 electrons could make a bond and we'd get our Br2 molecule. So make this a little cleaner. That would be our Br2 molecule. So each bromine would have what we call lone pairs around the outside. So a pair of electrons that's together and it's unbonded. And then we have a bonded pair of electrons. So we can count those electrons as well. We've got 2 here, 4, 6, 8, 10, 12, 14. So we've used all 14 of our electrons and created that single bond in bromine. Oxygen and nitrogen start to get a little interesting. So oxygen has those 6 valence electrons. I'm going to put my 2 unbonded ones on that side. So each one has 6 valence electrons. So we have a total of 12 electrons to use. You can see it's less than bromine, so we can't just do a single bond here. We've got, each one has 2 unpaired electrons, so those ones would bond together and form our 2 bonds. So oxygen is a double bonded molecule, and each one has 2 lone electron pairs or lone pairs. So that is our oxygen molecule. So hydrogen and bromine both have single bonds. So they each have 1 single bond. Oxygen would have 1 double bond. All right, let's look at nitrogen. All right, nitrogen, each one has 5 valence electrons, so we have 10 electrons we can use. You can see that it drops another 2 electrons going from oxygen to nitrogen. So you might suspect what that will cause. Here we have our 5 valence electrons for our nitrogen. You know what, I'm going to put my pair on the side just to make it a little easier. All right, there's our 5 valence electrons on each. So if we wanted to bond these, we would need to pair up those electrons. So that's a bond, that's a bond, that's a bond. We get triple bond. So to clean this up and make it look nicer, that would be nitrogen with its lone pair on each one. Okay, and we're going to look at kind of some rules on how we draw these when we get more complex structures. But our nitrogen here, if we look at it, we've got 1 lone pair, so that's 2 electrons, 4 electrons with the other lone pair, and then 6, 8, 12 with those, or excuse me, 2, 4, 6, 8, 10 with that triple bond. So that triple bond is 6 electrons total to make that triple bond. All right, so 6 electrons for a triple bond, 4 electrons for a double bond, and 2 electrons for a single bond. All right, so that's how we can draw our dot structures of our Hofbrinkel elements, of our diatomic molecules. The only ones I didn't draw were fluorine, chlorine, and iodine, and they would look exactly like bromine, Br2, because they're all in the same group. So they'd have the same structure. All right, now let's jump into trying some of these. So we are going to start with our list up here. I've got our steps. So we're going to start with CH4. We're going to determine the number of valence electrons. Carbon has 4 valence electrons each, and there's only 1 carbon. Hydrogen has 1 valence electron each, and there are 4 hydrogens. So we have a total of 8 electrons that we want to use, and we have to use all 8. So that takes care of step 1. Step 2, place the central atom in the middle and surround it by the other atoms. Well, we talked about that hydrogen cannot go in the middle, so we have to put our carbon in the middle. The other thing is that carbon wants to bond more times. Our chemical that wants to bond more times, we want to put towards the middle. Then we surround it by our other elements. I like to do 1 on each side, kind of like a box, kind of like our dot structures. So that's step 2. Step number 3, we want to single bond our atoms together. So our outside atoms, we single bond to our central atom. And now we want to count up our electrons because step 4 talks about leftover electrons. So we need to see how many we've actually used. Well, each bond, each line is 2 electrons. So we've got 2, 4, 6, 8 electrons used. So we have used up all of our electrons. We don't have any left. So we can't do step 4 because there's no leftovers. And we can't do step 5 because it says if any electrons are left. It's looking for leftovers. No leftovers. Step 6, if and only if the central atom does not have an octet. So this is where we want to check for our octet. Does our central atom have 8 electrons? And again, carbon has those 4 bonds. That's 8 electrons that it's sharing with the hydrogens. So carbon has its octet. If your central atom at that point and your outside atoms are all good, they have what they want, we are done. So if our central atom has an octet, and we've already fulfilled all the other steps, we're done. Okay, so this is called methane. This is natural gas. This is what's in your stove, what's in our gas lines in my classroom, that kind of thing. All right, CF4. So we're going to try another one. We're going to start from beginning with our checklist up here. So we've got carbon with 4 electrons plus 4 fluorines with 7 electrons each. So 7 times 4 gives us 28 plus 4 is 32. So we have a lot more electrons to use now. That's step 1. Step 2, place our central atom. Carbon can bond 4 times. Fluorine has 7 valence electrons, so it only needs 1 more. So it would bond once. So we want carbon in the middle, and we surround it with our 4 fluorines. That's step 2. Step 3, single bond everything. So 1, 2, 3, 4. There's our 4 single bonds. And at this point, I like to go ahead and check my electrons and just see how many I have left. So we've used 4 bonds. That's 8 electrons. 32 minus 8 would be 24. 24. Yes. So we have 24 electrons left. So step 4, add any leftover electrons as lone pairs. We have 24 left over, so we're definitely going to do this. And these are 2 dots put together on the outside atom. So we're going to do it on fluorine to start here. And we have 24 electrons. So as I go, I'll keep track of my electrons, how many I've used. And our goal here is to get each fluorine to have an octet. So they each have 2 electrons from the bond, so they need 6 more. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that uses up the rest of my electrons. And we completed step 4. We gave everything on the outside its octet. Step 5 is, again, asking if there are leftovers. We don't have any leftovers, so we don't have to do step 5. And step 6 is asking about our octet on our central atom. So carbon has 4 bonds around it. That means it has its octet. So we are good with that. We've used all of our electrons. Everything has its octet. We're done. Notice we haven't done step 6 at all yet. We've drawn 2 structures and not had to do any double or triple bonds. And that is very common. All right, let's do water. So water, 2 hydrogens. They each give us 1 electron, plus our 6 electrons from oxygen to give us a total of 8. So we want to start by start drawing by placing our central atom. Hydrogen can only bond once, so it's never in the middle. And oxygen can bond twice, so we're going to put it in the middle. And it doesn't matter which sides you put your hydrogens on. I'm going to go ahead and do my hydrogens like that. And I went ahead and single bonded them. A lot of times as you start to draw these, you go ahead and do step 2 and 3 kind of at the same time. So let's see how many electrons we've used. We've used 2, 4 for each, or total from the 2 bonds. So we have 4 left. So it says add leftover electrons as lone pairs to the outside atoms, except for hydrogen. Hydrogen's on the outside here, so we're not going to do step 4. If any other electrons are left, place them as a lone pair on the central atom. We still have 4 electrons left. So we're going to place them on oxygen, since it is our central atom, as lone pairs. As you're drawing lone pairs, it's important to make sure they look like a pair of electrons, that they're not just 4 free-floating electrons that happen to be near oxygen. We want 2 pairs on the sides of oxygen. So we've taken care of step 5. Step 6, if the central atom does not have an octet. So let's check it. We've used all of our electrons. Oxygen has 2, 4, 6, 8 electrons, 2 from each bond, 2 from each lone pair. So we have 8 electrons. That means this is done because it has its octet. All right, let's try 3 more chemicals. We've got NH3. So nitrogen has 5 valence electrons. We've got 3 hydrogens, each with 1 valence electron, so that gives us 8 to work with. Step 2, we're going to place our central atom in the middle. Nitrogen can bond 3 times because it has 5 valence electrons, so it needs 3 more. So it's our prime candidate for the middle, and we're going to place our hydrogens around it. And then step 3, we're going to go ahead and single bond those elements together. So we've used 3 bonds. That would be 6 electrons, so we have 2 left. So step 4, add leftover electrons to the outside atoms except hydrogen. So we get to skip step 4. Step 5, any other electrons are left, place them as a lone pair on the central atom. We have 2 left, so we're going to put them as a lone pair on the central atom. Step 6, we're going to check our octet. So we've got 2, 4, 6, 8, 3 bonds and a lone pair. That takes up all 8 of our electrons, and it has an octet, so we are done with that one. This is ammonia. This is close to ammonium. Ammonium is our NH4+, and we'll look at how we draw that later on in this section. All right, let's try the next one, HCN. So we've got a hydrogen with 1 electron, a carbon with 4, and a nitrogen with 5. So we have 10 electrons to work with. So this one, hydrogen can only bond once, so it has to be on the outside. Carbon can bond 4 times, so it's a good candidate for the middle. Nitrogen can bond 3 times, so it would be better to put our carbon in the middle and our hydrogen and our nitrogen on the outside. So the way they're laid out in the chemical formula is basically how we want to lay them out in our structure. So we've placed our atoms. We're going to go ahead and single bond them. Take care of step 3. Step 4 is to add leftover electrons as lone pairs to the outside atoms except for hydrogen. So we've used 2 bonds, that's 4 electrons, we have 6 left. Hydrogen doesn't need any, so we're going to add them to nitrogen to give it its octet. So it has a bond already, that's 2, plus 3 lone pairs would give us 8 electrons for nitrogen, and that would use up the rest of our electrons. So we've used all 10. And that takes care of step 4. Step 5, any leftover electrons? We don't have any leftover, so we're going to skip step 5. And 6, if the central atom does not have an octet, then lone pairs from the outside can be moved. Okay, so let's check our carbon. Does it have an octet? No, it doesn't. It has 2 bonds. That's 4 electrons. It needs 8. So we get to finally do step 6. It is the last resort. So we are going to move lone pairs from the outside atoms and share them with the central atom to create double or triple bonds. So we are moving lone pairs. We're not removing, we're not adding. So this lone pair here, and it doesn't matter which one I choose, if I move it to create a bond, I get something that looks like this. So let's see what happens here. Our hydrogen still has its bond, and it's happy with its 2 electrons. Our carbon now has 3 bonds, so it went from only 2 bonds to now 3, so it has 6 electrons. It's closer to an octet. Our nitrogen has 2 lone pairs and 2 bonds, so that's still 8 electrons. Nitrogen didn't gain or lose, it just is now sharing. So if we do that process again, we take another lone pair and move it, then we get this structure. And in this structure, hydrogen's still good. Carbon has 4 bonds, like it wants, 8 electrons. Nitrogen has 3 bonds, and a lone pair has its 8 electrons. And now everything has its octet. At that point, we are done. We've done step 6. So step 6 is only needed when our central atom doesn't have an octet. That is the only time. I hope that we're understanding that. Okay, our last one for now, H2S. So we got 2 hydrogens, each with 1 electron, plus sulfur, which has 6 electrons, giving us 8. So we're going to place our central atom. Hydrogen can bond once, sulfur can bond twice, so we're going to put sulfur in the middle, put my hydrogens on there, single bond them, so that takes care of steps 2 and 3. So we have 2 bonds, that's 4 electrons, so we have 4 left. We can place leftovers on our outside atoms for octets, but we have hydrogen, so we skip step 4. So anytime you have hydrogens, like a central atom and it's surrounded by hydrogens, skip step 4. Step 5, leftover electrons go on our central atom. So we have 4 left over. We're going to put those 4 on this chemical, or on sulfur. And that gives sulfur 2, 4, 6, 8. That gives it its octet, so then we're done. We don't need step 6. And we are done. We've used all of our electrons and we have an octet. Now if you notice, looking up on your paper at water, H2O, so H2S and H2O have this very similar structure to them. We might have rotated it or turned it a little bit, but they're the same type of bonding. They both have 2 bonds and 2 lone pairs. And this is because oxygen and sulfur are in the same group, so they're going to bond the same way. So now we're going to take a look at compounds that have more than one central atom. So we've looked at things that just have one central atom. Now we're going to double them up or add more. So let's start with C2H6. So 2 carbons, each with 4 electrons, plus 6 hydrogens, each with 1 electron, gives us 8 and 6, which is 14 electrons. Number 2, place the central atom in the middle and surround it by the other atoms. Well, this time we have more than one central atom. We have 2 carbons here. So we're just going to go ahead and place the 2 carbons down, and I'm going to go ahead and single bond those and use up 2 of my electrons. Then I'm going to surround these with the hydrogens. So we have 6 hydrogens. It's nice to have some symmetry as much as we can and spread them out evenly. And then we go ahead and single bond them. So that gives us, we've done step 2 and 3. So let's count our number of bonds total. So we have 1, 2, 3, 4, 5, 6, 7 bonds. 7 bonds times 2 electrons each is 14 electrons. That's our original amount. We've used all of our electrons, so this is done. If we look at it, our carbons each have 4 bonds, so they've got their octet. Our hydrogens are all good with their single bond. We don't have any leftovers, so steps 4 and 5 can be skipped. And since our octets are there, step 6 can be skipped. Let's take a look at another one, C2H4. So very similar, it has 2 carbons, each with 4 electrons, but now we only have 4 hydrogens with their 1 electrons. So we have 8 and 4 gives us 12 electrons to use. So we're going to start off very similarly. We're going to start with our 2 carbons. I'm going to go ahead and single bond them and use 2 electrons. And I'm going to spread out my 4 hydrogens. symmetrically, 2 on each, and single bond them. So at this point, we've used 2, 4, 6, 8, 10 electrons, and we have 2 left. So that's our first 3 steps. It says place our leftover electrons on the outside atoms. Those would be hydrogens, so we skip that. Step 5, if any other electrons are left, place them as a lone pair on the central atom. Well, we have 2 central atoms, but only 1 pair of electrons left. So we should give it to one of the carbons. It doesn't matter which one. So that's step 5. And step 6, if the central atom doesn't have an octet, then we can move our lone pair. So let's look. This carbon on the left has an octet because it has 3 bonds in a lone pair. That's 8 electrons. But the carbon on the right only has 3 bonds, so it does not have an octet. So we need to move some things around. We're going to do step 6. So we're going to take the lone pair, because we only have 1 lone pair, and we're going to move it to share between those carbons. So we're going to end up with the carbons double bonded with our single bonded hydrogens coming off of them. So if we look at that, we have used 2, 4, 6, 8, 10, 12 electrons. That was our original amount. Our carbons each have 4 bonds, and our hydrogens have the 1 that they want. So everybody is good on that one, and it's done. All right, let's check out this one, N2Cl4. So let's go through our process. 2 nitrogens with 5 electrons each, 4 chlorines with 7 electrons each. So 7 times 4 gives us 28, plus 10 is 38 electrons. It's a lot. Chlorine can bond only 1 time. Nitrogen can bond 3 times. So we're going to put our nitrogens in the middle. And then we're going to add our 4 chlorines. I'm going to do it just like I did my hydrogens. And then single bond everything. So we've used 2, 4, 6, 8, 10 electrons. We got 28 left. We got some space to fill in here. So we've done steps 1, 2, and 3. Our leftover electrons are going to go on our outside atoms. And since we don't have hydrogen, we're going to do this. So we want to add those leftover electrons as lone pairs. They each have 1 bond already, so we want to add only 3 more lone pairs. So that's 6, 12, 13, 14, 15, 16, 17, 18, 20, 22, 24. So that means we have 4 electrons left. Step 5, leftover electrons go on our central atom. So we can put 2 on nitrogen. That gives it its octet, 3 bonds in a lone pair. Oops. And the other nitrogen we can give a lone pair. So it has 3 bonds and a lone pair. Now, our nitrogens have their octet, our chlorines have their octet, so everybody is good. We don't need step 6. No double bonds here. So you can see how C2H4, similar in formula to N2Cl4, but we didn't need a double bond on the second one because we had plenty of electrons. All right, this next one's a good one, kind of different. We've got CH3OH. So more than 1 hydrogen, and they're separated from each other. We've got 3 over here and 1 over here. Well, what's the reasoning behind that? Our reasoning is that we want, sometimes our chemical formula wants to help us draw it. So sometimes they're listed or things are separated from each other to show how they're actually attached to each other. So what we're going to do is we're going to add up our electrons like we normally do. 4 for carbon, 3 for each for our 3 hydrogens, 6 for our oxygen, and then 1 more for our other hydrogen. So we've got 4 and 3 is 7 and 6 is 13, 14 electrons. Then we're going to use our formula here to help us out. I'm going to write a carbon, and then I'm going to put 3 hydrogens around it. And then the next thing I'm going to do is write my oxygen. And you know what? I'm going to go ahead and single bond those so I can start kind of seeing my structure. Now my oxygen then says after it has another hydrogen. So I'm going to add that hydrogen to my oxygen because it's showing that those are stuck to each other. So now let's count up our bonds here. We've got 2, 4, 6, 8, 10 electrons 5 bonds, so we have 4 electrons left. So we've done step 1, we've done step 2, step 3, we've single bonded everything, and we know that we have 4 electrons left. So it says to place them on the outside atoms. Well, hydrogen is on the outside edge of our whole molecule, so we don't need step 4. Step 5 is any leftovers, place them on our central atom. Well, carbon, let's look at it, has 4 bonds, so it has 8 electrons. But oxygen only has 2 bonds, so it needs some more electrons. So we're going to place our leftovers on oxygen. I don't know why those dots are so weird. And so now oxygen has 2 bonds and 2 lone pairs. We've used our 4 electrons, and it has its octet. So now carbon and oxygen have their octets, so we don't need to do step 6. This chemical is called methanol. It's a methyl alcohol. So our last one over here, CH2O, kind of got swallowed up in the structure in the pictures here. So very similar. We want to follow the pattern and draw it, but we're going to add up our electrons first. So 4 for carbon, 2 for hydrogens, 1 each, and 6 for oxygen. So we have 12 electrons. I'm going to draw it over here on this side using that same pattern. So I've got a carbon, and then 2 hydrogens are attached to it, and then an oxygen is attached to it. All right, so I'm just following the order that they're listed there. So that is 3 bonds, that's 6 electrons, so we have 6 left. So that takes us through steps 1, 2, and 3. Leftover electrons are going to be lone pairs on our outside atoms. We're going to skip the hydrogens, they don't get lone pairs, but our oxygen definitely does. It's got 1 bond, so it needs 6 more electrons. We've got 6 left. So now we've used up all of our electrons, so we can't do step 5. So let's check it out. Does carbon have its octet? Well, it has 3 bonds, so it only has 6 electrons, not an octet. So now we're going to move some electrons. We get to do step 6. So we're going to take a pair of electrons, doesn't matter which one, and we are going to share it with carbon. So that means we're going to end up with C and our 2 hydrogens. I'm going to kind of stick them off to the side like this. And then it is double bonded to oxygen, and that oxygen still has 2 lone pairs on it. All right, so there is our structure. All right, CH2O. And carbon now has its octet, oxygen has its octet. We've used up all of our electrons, so we're done. All right, I want you at this point to stop and practice. So in your packet, this is the end of these notes, but it's not the end of this topic. So I want you to get the basics down first of drawing these, and then in class we are going to look at polyatomic ions, so how do we deal with those, and exceptions to our octet rule. So besides hydrogen, who else doesn't get an octet, or who has more than an octet? So we're going to be taking a look at that in class so we can get a little more discussion in with that. Practice these. The other thing I'll throw out there is we did see a couple of these carbon-hydrogen compounds. Carbon-hydrogen compounds, we can build into longer chains of carbons. So if you have more than 2 carbons, just chain them all together and then start surrounding them with hydrogens, and that can help you too. All right, thanks guys.